Oi? Oi, Richard? Tudo bem? Ah, ok, beleza. Acho que minha internet caiu. Ah, beleza. Tá bom. O, o, o Jeremy chegou ou não? Ya. Ah, sí, 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 ya. Eh, Ah, beleza, sim. Ah, beleza, pode, pode. Tá bom.
There we go. Should we hear me?
I can hear you.
Oh, cool, fantastic! Yay, getting there.
Okay.
Okay, so let me see. I'm gonna share the screen for now. Screen. We go. And you should be able to. Okay, so poof, where am I? Okay, so I don't see myself right now.
No, it's fine, it's fine.
Okay, so you should be able to see me.
Yes. So
Well, I'm ready whenever you are.
I think we're going to wait a couple of more minutes.
I can tell. What I can tell you is that I'm just for those who don't know me, I'm Jeremy Riousset. I work at Florida Tech.
Oh, no, wait, Jeremy, let me do the introduction first.
Okay.
Before you
Okay.
do all of that.
Okay, so let me just, I'm posing for now and...
Tá bom. Sorry, yes.
That's okay, no problem.
Oui.
Oui, oui.
Oui, oui.
We don't say oui, oui, we just say oui. But according to my wife, we do say ooh la la.
So, you don't say, okay, I have a question. Is it weird when people say things like touche?
Well, we don't say it with that meaning in French.
Okay, yeah, because it's, for us it's touche, but for you it's like I touch you.
Yeah, and the thing, no, it's more like owned.
Okay.
And actually, we would use owned.
Oh, okay.
But yeah,
no,
in general,
you cannot use that word in English too much.
But the thing is, I can't pronounce. I don't know how to say touche in English. I don't know how to pronounce it the way it's been corrected, so it's interesting. Ricardo.
Hi, Jaime.
Hey, how are you?
Nice to meet you.
So I shared invitation with a few people. I don't know if they'll be able to make it. So
I think, well, yeah, I think it's up to Richard to let them in, probably.
Yes.
Okay.
So you may see. Well, you remember Josh, Jaime?
Yes.
So I forwarded because we were working on a proposal.
Okay.
And, so it's something I thought it might be of interest, and a few students of mine, including prospective grad students. So
okay. So
if you see random people that you don't know, it's possible. Hopefully it's my students, but students are students. So
okay. Or Richard.
Richard.
O Jeremy compartilhou o link da apresentação para um par de colegas dele e um par de alunos dele. Então, por se você tiver como algum endereço de e-mail não reconhecido da USP, se puder você deixar para eles entrar. Ah, beleza, beleza. Ah, beleza, beleza, tá bom. Ok, bom.
Muito bom, Richard.
Ok. O Richard.
Chat. Okay, the chat is here.
Richard?
The chat.
No, I was talking to Richard. Richard. Acho que a gente já pode começar. Ok, beleza. Bom. Então, let me just turn my camera off. Jeremy, I'm going to introduce you. In the meantime, you can start setting up, like you can start presenting. Ok, so, boa tarde, pessoal. Para quem não conhece minha voz, eu sou Jaime, sou do grupo de sismologia do Voyager. Hoje a gente vai ter esta palestra do professor Riousset. Eu convidei ele porque, na verdade, acho uma palestra muito bacana. Não é relacionado com sismologia, mas como por ser de ciência planetária e como integrar tantas ferramentas de outras áreas, eu achei bacana para a gente ver alguma palestra um pouco diversificada. Bom, o Jeremy, ele é de França, ele se graduou de um programa doble de engenharia em França, o École Centrale de Lyon. Depois disso, ele foi para os Estados Unidos, ele fez o mestrado, o PhD em engenharia elétrica de Penn State University. Ele fez seu primeiro trabalho de dissertação lá em simulação numérica de raios e relâmpagos e descargas de jet. Para o pós-doutorado, ele foi primeiro para Georgia Tech, que foi lá onde eu conhecia ele. Ele não só fazia pesquisa lá, também ajudava estudantes desorientados na vida como eu. Depois disso, ele foi para Braunschweig, na Alemanha, e foi lá quando ele mudou um pouco mais para a ciência planetária. Nesse momento, ele está na universidade, no Florida Institute of Technology, chamado Florida Tech, e ele actualmente trabalha en breakdown eléctrico de teoría de lightning, blue jets, unos negocios que se llaman gigantic jets, comparative planetology y en particular o estudio de los rayos dentro de la Tierra, Júpiter, Saturno, Marte también, y también de cómo interactúa o viento interestelar con la ionosfera dos planetas. Bon, okay, Jeremy. Since you didn't catch all of that, I hope that it's okay.
Yeah, no, I got most of it.
Okay, cool. Okay, so take it away.
That was. You can go.
Okay.
You told me go ahead, right?
Yes.
Okay, sorry. You said it in Portuguese, so.
Sorry. Just.
That's okay. So yeah, I'm Jeremy Riousset. As you may tell from my accent, I'm French, which at least give us a common point. If not the science, the symbol of the Corinthian is D'Artagnan, which is also from south of France. Not the same south as I am, but at least we share that. But most importantly, that means that I have an accent and I can speak fast. If you want to interrupt me, there is absolutely no problem. I did a lot of the presentation to introduce Martian lighting and why am I interested in something that is still utterly theoretical. I call it life spark or death stroke because lightning has two meanings, and we'll go into that in a little bit. So first, I'm going to give you a few statistics. When I first created my talk, I was looking at mostly US data, but I was able to find, thanks to publication by Brazilian experts, some information about Brazil that I would like to share. But because this also is not necessarily plasma environment, and the research group are focusing more on seismology, I'll take quite some time to explain what is a lightning and what are the type of lightning, and how we go from what we know from Earth to Mars and to another planet like Venus. I'll try to touch base on a little bit on what I currently do and my most recent work on understanding Mars and Venus environment and compare it to Earth. So let's start a little bit with some statistics. And why do I chose the title Deathstroke and Spark Life, or Life Spark? Essentially because lightning is known as a killer of cattle, a killer of people, and at the same time, a very famous experiment called the Miller-Urey experiment. Sorry, I heard a beep. I do not have the chat open, so please unmute yourself and ask a question if you want to interrupt me. Okay? So on the left-hand side, I added this. This is an extract, an article that was published in the Scientific American Brazil, and thank Google Translate for that. If you want, I can share the PDF, but what I will look into is a little bit of statistics. And the beauty and great thing that Brazil has is it has a very good group called, now forgive my Portuguese, the Grupo de Eletricidade Atmosférica in São José dos Campos in Sao Paulo state in Brazil. So in Brazil, and that's where I got some information from this author, Yara Cardoso. Again, forgive me for my Portuguese, and one other colleague of mine, which is Fernanda Sausabas. So I'll use that to try to put the knowledge we have in the context of Brazil. So I was able to find this map. Hopefully you recognize the Brazil and several, I think so, states, and you can see that that's the number of cloud-to-ground lightning density. How many lightning hit the ground per kilometer square in a year? And you see that in the region of Sao Paulo and the coast, it's the highest in Brazil. It's among the highest in the world. Roughly 8 cloud-to-ground lightning per square kilometer per year. So I would like to, for one of you to answer. When you think about lightning, if I ask you in a Brazilian storm that's going to last, let's say, an hour, how many lightning flashes would you expect to see?
I'm going to say 60. I don't, just not knowing anything.
That's actually a pretty good estimate. It's multiple times per minute. Most people make the mistake to think that, oh, I see a storm, I may see like 4 or 5 lightning total, but actually you have a frequency during a storm that can be up to, I don't know, 10, 20 per minute. So you have one every few seconds. Here you'll see the first acronym that we'll use, CG. CG means cloud to ground. It is worth stopping for a second right now to realize that lightning, as we understand it, it's a very small fraction of the actual electricity in the storm. There is about 80% on average of the lightning which are invisible, well, which you will never see individual channels from. What you will see is just the cloud becoming very white and then dark again. And just those are called lightning that are intra-cloud because they will never escape the cloud. So what we typically see and what we call lightning is just that small fraction, that small branches that goes to the ground, but it's only a small fraction of what we see. I was also looking a little bit of, again, statistics. So on the left-hand side, you can see where in Brazil you have more lightning activity. It's pretty simple. It's where you have more storms. To get storm, you need water, you need heat, and you need some dust, some nucleus, something to create the rain. Well, Sao Paulo is a pretty good region for that. And actually, I believe if it's not the first or the place on Earth where there is most lightning, it might be the second highest, with actually where I'm located, Florida. Within Brazil, there is I look a little bit at the numbers. You can see the number of deaths. So that's for a decade. And you can see that in Sao Paulo, in the city of Sao Paulo, there was about 230 people who died from lightning between 2000 and 2009. So it is actually at least twice more than anywhere else in Brazil. So just be careful. So why that? It's actually quite interesting to think about it for a few reasons. The first one is that if you take this number, total number of lightning in Brazil, a person who died by lightning in Brazil during that decade, you have over 1,300 people who died. Divide by 10 years, you have about 130 people who died by every year because of lightning in Brazil. It's interesting because if you compare this number to what happened in the US is about 5 times less, so it's about 30 to 40 people. The population of Brazil is about 200 million. The population of the US is about 320 million. So what it tells you is that, in general, every year, you can say that in Brazil, you have one chance out of 1.2 million to be struck by lightning. If I do, well, actually 1 per million, roughly give or take, let's do a Fermi problem. I say one chance out of 1 million to be hit by lightning. If you multiply that by the average lifespan in Brazil, 75 years, you get roughly 1 out of 13,000 chance to be hit and killed by lightning. Just for fun, I looked. You have actually one chance in the 50 millions to win Mega Sena. So what it tells you is that you have about 40 times more chances to die from a lightning strike in your life to win than to win at Mega Sena this year. So I'd say don't play the lottery, but it's just me. But the numbers are, as far as I can tell, are accurate. Another interesting fact is that we look at the number of people who die. There are a lot of factors that to take into account. People that work outside, obviously, are more subject to that. People that work in field, and men about 4 times more likely to die from lightning strikes than a woman. So it tells you one thing. When a man sees a lightning storm, he goes outside to see the lightning. When a woman sees a lightning storm, she finds shelter inside. And that's probably the main reason why lightning is sexist when it comes to killing people. It's an interesting fact. So just, if you see lightning, stay inside, or do what I do theoretical studies. So that is why the typical image of lightning is that of a very lethal process. However, it's also quite interesting to think about really an image. I don't know if I kept it. No, I didn't keep it. But if you think about the image of Frankenstein, life is created is the creature of Frankenstein Frankenstein becomes alive when it's hit by lightning. You always have these flashes and these sparks all over the place. And actually, that is not completely wrong, because there is a very, very famous experiment called the Miller-Urey experiment in the 60s, and actually in the 50s, that was able to turn basic gases like CO2, nitrogen, etc., and by circulating them in an environment where sparks would occur, they were able to create amino acid. So the very first basis that would then become DNA and create life. So the idea that a spark and lightning might have played a role in creating life is also interesting. But there is a caveat. The caveat is quite simple. It just say, how do we define life? Because the only thing we always do is defining life as what we know. And even in what we know, creating a definition is tough. I'll show you why. So basically it's an organism characterized by the capacity for metabolism, growth, reaction to stimuli, and reproduction. And it's very easy to break that definition, because if I ask you, think about fire. Fire will grow if you put more fuel in it. If you take a stick and shake it, it will react. If you split it and put it somewhere else, it'll grow again. So it will reproduce. So by this definition, your fire can be considered as alive. Another even more interesting example would be the pile of dishes in your student's sink. They eat, they put the plate, they add more, so the pile grows. It gets more dirty, so it metabolizes. If you push it, it crashes, and if you split it, it's grow even more. So technically, by that definition, by the Merriam-Webster Dictionary, the pile of dirty dishes in a student dorm is alive, which makes sense sometimes when you look at what's on those dishes. But that's simply a way for me to emphasize that defining life is extremely difficult. And yet, I'll be honest, that's an argument I use whenever I try to explain the importance of lightning in research. Most people simply ask me, how do we harness the power of lightning? Well, the problem is that harnessing is one thing, but keeping it is much harder. We need big batteries. I've alluded to a few times to what's called the Miller-Urey experiment. So let me explain a little bit what this is. So there was a nice animation. Let me see if I can. Oh, there we go. I want to go back to my arrow and start a video. So it's a small video that shows the setup. So what you have is water, methane, ammonia, hydrogen, so fundamental Earth. You put them in a flask and you basically warm it up and you make them, you create circulation. You heat the water, create evaporation. The evaporation will then move around, and at some point in the system, you fire a spark. So you can see your water moving the gases. The gases reach the chamber. In the chamber, you create a spark. Okay, spark will modify chemically the arrangement of the atoms, and ultimately will create what's called these amino acids. So you can see here the bubbles of ammonia, of methane, and from hydrogen entering the chamber. Sparks occur, and when we look at what's going on, what's transported and filtered, we will find amino acid. So that's called the Miller-Urey experiment. So it's really interesting to see that the whole process would be completely pointless without lightning. So that's the two sides of lightning. Oh, that's my spark of life, by the way. I did have the video. You can see the Frankenstein, and how do we associate also lightning as the beginning of life. So, two sides, lethal and necessary for birth. We saw that sometimes words can be a little confusing. Basically, life is a difficult thing to discuss. So let's look a little bit at what is lightning and what do we call lightning. Lightning is a discharge process, and a discharge process doesn't really help much. It simply means that it's an avalanche of ionized particles. The ability to create that one ion or one electron can knock an electron out of another particle and create ultimately two ionized particles, etc. The level of ionization, so if you have a lot of ions inside the gas or a lot of free electron in the gas, that will create the discharge process. And then you have the visible part, which is the light emitted during those ionization mechanisms. It's also a discharge when you have a high level of ionization, because, for example, the solar wind is a plasma, but it's lowly ionized, and that's why we don't call it a discharge, because a discharge also involves high ionization and short term. It cannot be a continuous thing. A continuous thing is not a discharge. So those are a few things. But by this, we also should emphasize that there is a lot of variation. So we're going to look at a few things. When we look at the plasma and where we can see ionization on Earth, we have a bunch of scenarios, and I'm going to emphasize a few and see which one we're going to work on. We're going to see Earth as the most natural ionization you'll see is your aurora. That's what you see in this top panel. It's also a very weak one. It's long-lasting. It's not really a discharge. When you look at medium ionization, then you have a quantity of discharge which are related to lightning but are not really lightning. They are called streamer discharge, and I'll go into a few more details in a minute. And if you have really something with a lot of energy, a lot of ions, then we have the lightning. Actually, that I'm going to brag, but it's something that I co-authored about 12 years ago, actually, and that was our article was published in Nature Geoscience. It's really cool. Now, is it the only place? No, because we can actually go a little further and look at other planets. There are quite a few things that are really interesting. So aurora are easy to detect. You find them on Jupiter. You can find them on Mars, but in different wavelengths. Medium ionization is a good question. Here you see what's a devil storm, and we'll spend some time explaining what these dust devils are doing and why they're interesting. And that's actually a picture of Mars. So Mars has possible some form of lightning. And then there are clear lightning that I forgot if this one is Jupiter or Saturn, but Jupiter, Saturn have clearly the clear signature of lightning. So really, so that's an example of gas giant lightning, so detected by Galileo and by Cassini. And finally, almost everywhere in the universe, you have the interaction between planets and stars through the solar wind. And that plasma is actually so abundant that it represents overall 99% and change of the baryonic matter. So of our universe, if you look at I'm talking the known matter of the universe, the known matter, not the dark matter, not dark energy, just classic baryonic matter. Well, over 99% of it is in the plasma. Hence why we should study plasma physics. At least that's what I try to convince my students of. So, going to lightning, really. So lightning is a transient, high current electric discharge with path length measured in kilometers. So a few things here. Transient, so not like a solar wind. High current, that means a lot of ions are flowing, so very large. Discharge, so transitory event, with path lengths measured in kilometers. So basically a process that is really large, because a spark can also be seen as a lightning. And the reason we compare a small spark like the one you see on your shirt when you take it off in the winter, if you ever wear a wool shirt in Brazil, well, those are the same process, and the process behind it is called the leader discharge, which is the highest, strongest type of discharge. So let's look at some events that we got from lightning. So looking at some high-speed images, we can see why we call it transient, why we call it high current. Oh, that's not a pen. So you can see high-speed videos and kilometer scale discharges. What I like in these high-speed videos is that it reveals that what we call lightning is actually not the lightning itself, it's a return stroke. Basically, what's the most visible, it's when the lightning has already hit the ground and is creating this path between the ground and the cloud. So I'll show you again. You can see it's brilliant, it's bright, but the brightest moment is right when it connects to the ground. It's just simply a short circuit process. So that's one, can tell just from the image, it's powerful, it's energetic, it's everything you want. But they all come from the same initiation, the avalanche process. So what happened? You take two electrodes, you put an electric field behind them, and basically the electric field is going to pull the charge, the electron one way, the ion the other way. When you do this separation, you have an ion. The electron has now high energy and is accelerated in the electric field. It's going to collide with another particle and eject another electron. So basically, we can see that one ion right here, pointer, there we go, releases an electron. The electron hit this particle. The original particle in orange is going to hit another electron, another neutral, and continue. And the newly created electron now hit another one. So we had one atom turn into an ion. The ion is now creating two more ions. Each ion creates two more ions, etc. So we have the avalanche. This is called the Townsend discharge. Basically, it's this exponential growth of the discharge. Depending on how many of these events we can have multiple options in terms of discharges, and all those things I've showed you before, the lightning, etc., they all come from that. It just depends on how many you have. So what do we have? What kind of element do we have? Well, we have the electric fields, and the electric fields are going to tell us a few things. In particular, that they define what kind of process we have. Without going into many details, to be able to create these avalanches, we're going to need to have a certain amount of volts between each in our chamber. So I'm going to go into what's a little more interesting is why Mars and what's interesting and how do we get there and what's useful for it. And so actually, I'm not sure. Well, I'm going to show you and comment on that video. That video is actually a description that first introduced this new lightning that we have. This new lightning, sorry, I have the sound here, but basically it just tells us that we have the common lightning that we've seen in the past, but also new discharges. And that is the first one we see, a lightning that goes up. That's a jet. A jet going up. Another jet is going up. And so another element here is a sprite. The sprite is simply also a different type of lightning. And these two type of discharges that I'm going to go over maybe at the end simply are derived from lightning. And unlike what this video suggests, they are not powerful because their scale is much larger, but their energy is not proportionally bigger. So what do we have? Well, we can have discharges that are not as intense as lightning, but a lot bigger. So the next thing I'm going to show you is called a sprite. It's an event that starts around 70 or 80 kilometers above the surface. It's about 60 kilometers from top to bottom and about 80 kilometers from side to side. It's called a sprite. But unlike lightning, it is not a very energetic channel. It's just a weaker kind of discharge. And let's look at one in a high-speed video. So that's a high-speed video where you can see what's called a carrot sprite, where you have these nice channels going down and this beautiful hair or halo on the top. And that's a sprite. It's also a discharge. It's very short-lived, a few milliseconds. It's clearly defined, clear channels, but very different energy. Actually, NASA, no, I don't know if it was NASA, but they tried to associate that with the destruction of one of the shuttles, and then realized that if you were to cross that, the chances that you would actually be shocked are pretty small because it's very low energy. But these have clear signature. They are discharges, and they are important because they appear at low density, much higher altitude, which have comparable, where the pressure is similar to what happens on Mars. So let's continue. Another one is a gigantic jet. So it's the same kind of thing as a sprite, meaning it's a relatively weak discharge, but instead of going down from the top, it's going up from the cloud. So we'll see one. That's the first one that was detected. And here you can see the channel. So it's going to play again. And from the bottom here to the top, it's about 70 kilometers. And here, invisible at the lower part, is the actual thunder cloud. The thunder cloud, that is the origin of this process, and it developed from a normal lightning, and all of a sudden it goes up. I don't know if I have one more. Yeah, a blue jet. Again, here it's a view from afar, and you'll see how the cloud now allows creation of lightning. So I'm going to actually go directly here. And you can see this fountain of light. I'm going to go back again. You see the fountain of light in the middle of the image, which is similar to the previous case, but you can also tell that this fountain of light is indeed not as intense as the lightning. It's a lot more diffuse. And it's really, really important because this intensity, the strength of the discharge, will define whether or not we can detect lightning on other planets. So here we go, a small summary. What have we talked about? The classic lightning, the one we're familiar with, this one, cloud to ground. The blue jets, which are this small fountain that goes about to 40 kilometers, weaker than these channels, more diffuse. Here, bigger, you have the gigantic jet, which the lower part may be very intense, but the upper part, seen here, is a much weaker discharge, less energy per volume, per unit volume. And then the sprite, which is essentially starting here and developing filaments downwards. So this part and this part are discharges that we call streamer, as well as this. The lightning itself, which is more intense, is leader discharges, and probably the root also of the gigantic jets. So with this in mind, we're going to go to another reason why I want to I have an interest in Martian lightning. What do we have? If I look at the lightning, that is this one is your classic sandstorm. Classic thunderstorm. So the one you should be able to see any moment. Oh, there we go. Let's see here. I'm going to go in a second. And there we go. We've seen the lightning. So that's the classic discharge you see in a thunderstorm. So again, if I look at it, you see the clear branching going to the ground, everything else inside the cloud. But Mars has a big issue, very, very little water. So is that the only way I can see it? Well, if you look at an event in Chile, you can see that lightning also occurs with volcanoes. Why? Because volcanoes provide the heat and the water and the dust to create lightning. Similarly, another view, both are Calbuco in Chile. You can see the eruption, and I don't remember if this one shows as many lightning. Hopefully it will. Yep, there we go. You can see the lightning. This is lightning. So you see a few. Another one. All these little bright spots are lightning. So that gives us a few hints of why to look somewhere else, fundamentally because in the solar system there are volcanoes. So why Mars? Well, Mars is very interesting for multiple reasons. The first one is it's possibly habitable. It has some water, it has some electricity, and has volcanoes. And you also have an unshielded atmosphere with no magnetic field, and it's easier to create the beginning of the avalanche in this condition. So Mars would look like, so that's us in definition of the habitable zone. Let me just take my laser pointer again. So here is Earth. Mars is somewhere here. So technically it's still quite habitable. And we would like at some point to get there. But does it have water? Well, if we look at the structure and we compare it to some structure on Earth, we see this structure that suggests that you can have water that flowed on Mars, either in the past, and many features looks like coastline. And actually, one exercise I did with some students of mine is say, well, imagine that you decide that you look at the average height of Mars, average radius, create a sphere, call that the areoid, and look at color in blue whatever is above zero, and in below zero, and in blue in copper what is above zero. And if you do that, you have this image that basically tell you that Mars has a lot of coastal lines and features that would resemble water. In particular, this Valle Marineris right here. You can see how it looks like a delta. So another very important thing is on Mars, you have dust events. And when I say dust event, they are significant. That is a few months. So from June 26, 2001 to September 4, 2001. Same planet, same image, same conditions, same observation. And you can see how a dust storm has rendered the planet completely opaque. So it's a sandstorm that has a scale of the planet. This is interesting because if we look on Earth, we have dust storms. So that is, unfortunately, it's not very visible, but this is what's called a dust devil in Israel desert. And this is what, and that is the Mars equivalent to a dust devil. And if I go back to a few slides before, where was it? All right. But you see here, I thought it was, I'm sorry, I remember my slides improperly, but that is sandstorm. So that lightning that we were looking at earlier, here, is created by sand. So a sandstorm on Earth creates lightning. Dust storm on Mars, we don't know. So we have water, we have sandstorms, we could have lightning, so with the water, with the lightning, with the CO2, we could have life. So that's a good reason why to look at Mars. So in addition, we also have a bunch of volcanoes. So another exercise I did with my students, now you remove the water, you exaggerate a little bit the geology, and you can see the volcanoes. So that actually Olympus Mons and the Tharsis Mons. If you look at that, I don't know if you see my camera, but basically we did that, we printed it in 3D, and you can see clearly where the volcanoes are. And with such volcanoes, you expect to have massive eruption. If you have massive eruption, again, you have a good reason to think about it as a possible source of source of a volcano of lightning. But the biggest problem is, as much as we think there is sandstorm, there is water, there is heat, there is an electrical circuit, there is a million reasons why we should have lightning, we haven't found it so far. There is one case where we think that we have observed it, but it's never been reproduced. One of the reasons, I think, is because what we've looked at is the same lightning that we have on Earth, the one that are very powerful, the one that are very strong, that have a strong electromagnetic signature. But if we were to look at other discharges, then we probably could not detect them with the current instrumentation. So part of my studies is to think about it as, well, what does it take to create lightning on Mars? What would it look like? And what do I need to detect them? Another case, let me see if it's worth for me looking at it. Yeah, actually, I do have a little bit of time, so it's good. So we're going to look at Venus. Why? Because I really like Venus because it's a perfect compromise between Mars and Earth. It has the size of Earth, but the atmospheric composition of Mars. If we look at our sketch, it's not too far from being habitable. So if I look at my laser pointer again, so my Venus is, where is Venus? Where is it? So I have Earth here and Venus is here. So if we look at the optimistic habitable zone, well, Venus is not too far. And in particular, the atmosphere has probably evolved through time. So if it's evolved through time, that means that I can probably look at what could possibly be the reasoning for it. So we have a couple of images, and we can imagine that, well, in different time, you could have Venus that looks like that. It's similar to what I did with Mars. These are images from NASA, but if you fill up the water, you can find coastline, and you can have a climate, and you can have lightning, and if you have lightning, you can possibly have the initial spark for life. It also has a bunch of volcanoes. So this, I don't know if that moves. Yes, it does move. So that's an image of the volcanoes on Venus. And that's an exaggerated view, but those are basically volcanoes from Venus. So volcanoes, we know, can also be source of lightning. So it's really an interesting cases where we have the volcano like on Mars, we have CO2 like on Mars, we have an atmosphere much stronger, so more comparable to Earth. So it's really a good case study. It also has quite an interesting aspect because if we look at Venus, we have a lot more clues that there should be lightning. And what's worth looking at is where would those happen? If we look at the clear atmosphere, unlike on Earth, the clear atmosphere, the clouds are not near the ground. If we were to scale Earth, basically you would see clouds roughly up to here. Okay? But what we would see on Earth, or in Venus, are more signature in this here, the cloud deck. So it's worth asking ourselves what conclusion can I draw, and how can I compare those different studies? So that's what I'm going to do. I'm not probably going to not touch much on coronal discharges, but I'm going to take a few minutes for that. To create lightning, you have what's called the $1 million question: how to start. The easiest way to think about it is if I am able to create ions quicker than I destroy them, then I can create the avalanche and I can create lightning. Mathematically, you just say the ionization coefficient is greater than the attachment coefficient, and you look at for which electric field that happens. Without going into much details, this is basically solved using a probability distribution function. And if you have questions, you can ask me. So when you do that, then it's a little more interesting to look at plots. I say, you know what? Let's look at what the Earth atmospheric composition of Earth. So that basically what you have here. That's the number of particles per cubic centimeters as a function of altitude. Okay, that's panel C. If you scale that to the proportion, you can see that almost everything is this vertical green line here. That is your nitrogen. Sorry, blue line is your nitrogen. It's almost everything. Green line is nitrogen. Brownish line is oxygen. So it's about 20%, nitrogen 80%, and then atomic oxygen, the upper region. If we look at the lightning activity on Earth, it occurs basically between 0 and 100 kilometers, 0 to 20 for lightning, and up to 100 kilometers for other discharges, weaker discharges. We can look at the temperature profile to find roughly where this is. And we can do some calculation to see what is the value of the electric field at each altitude and to be able to create those discharges. That's what's shown here. So you can see here that we have a few ways to calculate it, but fundamentally, the electric field to start a discharge is proportional to the density. So that's what we're looking at. So with that, we have a few things. We see where the pressure is low. We see the kind of environment we have. I can take that and look at what it looks like on Mars. If I do the same thing for Mars, I can see, well, if there are lightning, I can look at how tall these dust events are. I should see something within the first 50 kilometers. Well, within the first 50 kilometers, your atmosphere is essentially carbon dioxide. So if you look at that, you can calculate in carbon dioxide what is the electric field I need to create this spark, this initial moment. I can do that. I can look at it and look at the value and see, actually, it should be much easier than on Earth. On Earth, I need roughly 30 kilovolt per centimeter. So in a centimeter, if you apply 30 kilovolts, you have a spark. On Mars, at the surface, you need only maybe 100 volt instead of 30,000 volt. So in CO2, it should be much easier to create this discharge. And yet we don't see them. And we should, because everything there tells us it should. So my curiosity is to know, are we looking at the right thing? Are we looking at lightning, or are we looking at something else? Every experiment we do on Earth in low pressure, in CO2, tells us there should be something. And that's really a question, why we think there should be and it's not there. And the other one I like is Venus. So if in Venus, if we do the exact same thing, it's mostly CO2. I can calculate the same thing. How much electric field do I need to create the spark? I do that. There we go. We start. We have our lightning. Good. But to have this spark, I can see that the value decreases with altitude and becomes much easier in higher level. And when you look at what value you need in the cloud region of Venus, so here you see in this second panel, you have the vertical altitude and the temperature. And for illustration purposes, I show where the clouds are, the H2SO4 cloud. They are right here. So that's where lightning should be. That corresponds to actually the same pressure that we see on Earth and very similar condition for triggering lightning. And on Venus, we have seen more hints that there is lightning. So really, we are in that situation where Venus should have lightning and it doesn't. Oh, sorry. Mars should have lightning and it doesn't. And Venus, well, we have hints. It seems it should be, and yet we are not sure why, because the clouds there are different. So what I do like is to think about, to compare things. And the problem is that if you just look at the number of volts per meter you need to create lightning at various altitude, which is what the left panel shows you. Well, you can see that they decrease with altitude, okay, 0 to 250 kilometers, but they are very hard to achieve on Venus, very high field, so need for much stronger mechanism. They are intermediate on Earth and quite easy on Mars, but it doesn't help us to compare each other. So what we take is, well, if I assume that I divide everything by the pressure, then the condition on Mars and Venus should line up, and Earth should be different. Why? Because if I remove the pressure, then both Mars and Venus are just CO2. So if I do that, it's called the reduced breakdown field, I can see that Venus and Mars are extremely similar. Why? Because they are just conditioned to create CO2. It's create a spark in CO2. Earth, on the other hand, is much higher. Okay, there is about a factor 40% difference. So it should technically be harder to create a lightning on Earth than it is on Mars. One thing that bothered me when I create the simulations is why I still have differences between Venus and Mars. So what I looked at is what are the critical, really important elements, and it comes to the fact that if you want to create lightning, a small amount of atomic oxygen helps a lot. Venus doesn't have that. Mars does. And Earth does as well at high altitude. And if we look at when Earth has that, it's actually in a region where we observe some of these much weaker discharges, these sprites that are big but very little energy. So where we have a little bit of atomic oxygen on Earth, then it's easier to create lightning. On Venus, we don't have anything, but on Mars we do have atomic oxygen, and we may ask ourselves, does this atomic oxygen also support the idea of having the kind of discharge that occurs on Earth when you have this element? So I'm going to skip that because Paschen curves is a continuation of that, but looking at various geometry. So I'm going to just go a little bit further and show you, just summarize why I looked into that. So why are we looking at lightning? Because electricity is necessary, is a sufficient but not necessary condition for life. So basically, it would help to have it. We can create light. Actually, I think I did it opposite. It's a necessary but non-sufficient. You can have lightning and no life, but as far as we know, we're going to need lightning to have life. And if you want to understand life on other planets, well, we have to understand lightning. Lightning may be natural, but it can also be created. When you create a spark, that's what happens. And why is it important? It's because when you create a catalyst, then you create a situation where you create a danger that was not present. The easiest example is why lightning hits lightning rod. It's because a lightning rod creates a condition for a lightning connection. When we're going to put a rover or a station on Mars, we're going to have this big antenna, this I think it's whip antenna, huge whip antennas, to be able to communicate with Earth. And at the tip of this antenna, the electric field is increased. So without the antenna, there might be no lightning, but with the antenna, we may actually be the reason for lightning, and we may destroy the habitat. So we need to protect the rover, the bases, everything. This lightning observed everywhere throughout the solar system, and we'd like to know how they vary from one in the other. And in Venus and Mars, we'll see it. We are particularly interested in it because it's comparable to us. But the question is still open. So that's why I still work on that. And I hope to continue. Well, I thank you all for your attention. And I'll be happy to take questions. So there we go.
Thank you, Jeremy. If anybody would like to ask a question, just feel free to Feel free to interrupt me. If not, I will just ask some questions from a person that doesn't know.
May I make a question?
Go ahead.
Jaime?
Yes, of course.
Jeremy, thank you very much for your talk. Very interesting. Very, very nice. Thank you a lot. I was wondering if we know that early Mars likely had liquid water, isn't it? Is it possible that lightning was more likely to happen in Mars in the early million years or giga years than today? And then is that possible?
It is more than possible. It's very likely. So one thing is, it would be significantly easier. A few things that are interesting is if you look at the temperature profile, the temperature profile on the planet depends on a couple of things. It will depend on the atmospheric density and obviously the life of the sun and the magnetic field. That's another part I did not touch. So about, I think it's, 3 billion years ago, 3 to 4 billion years ago, the core dynamo that creates Mars magnetic field disappeared. It has several consequences. The first one is it exposed the atmosphere to the solar wind, and basically that's how Mars lost about 96% of its atmosphere. Mm-hmm. The consequences is with no atmosphere, you have no greenhouse effect. If you have no greenhouse effect, then you have no you have either two effects. The first one is you're going to have an evaporation because you have lower pressure, and you also have freezing. Temperature is going to cool down. So if anything, water is going to freeze, and that's why we see it at the pole. So to answer your question, in a wet Mars, with a stronger atmosphere and likely a magnetic field, we are closer to the current environment. And I would say yes, because we have a day-night rotation. We have therefore great temperature gradient that allows us to create vertical updraft. Vertical updraft will take water from the surface, freeze it, and through what's called the collisional mechanism, create cumulonimbus. This will create lightning, and there was actually one thing I'm more inclined to believe is that if we're looking for life on Mars, it's likely to be past level because of what you described. Conditions were likely to be extremely good to create lightning in the presence of organic molecules.
Yeah, that's interesting. I have another question that it follows from this. Mm-hmm. Do you think that in this wet Mars, it would be easier to produce lightning than on present Earth, or more difficult?
And
something if lightning would be limited to certain latitudes, or it would be distributed along the whole planet.
So, assuming that the atmospheric composition is mainly CO2, it would be still easier. The planet being smaller, it has a smaller gravity, which also means that the cloud, the pressure would be lower, and in general, lower pressure make it easier to create a lightning. And if you think about one of the last graph I presented, I also showed that CO2 compared to air is significantly easier, about 40% easier to create lightning in it. So the caveat would now turn into the meteorological process that will be needed. So having the atmosphere, having the water is one thing, but having the Hadley cells, having the same type of cloud is more difficult. And in terms of thinking where they would occur, most likely they would be around the equator. Just if I draw a quick analogy with Earth, They would be around the equator, and they would be above the ground for two reasons. Above the ground because it's where the updraft is stronger. If you have a wind, you're going to hit a mountain, and simply mechanically, a wind from a surface that will be hot will go up, and with it raise water, creating cloud more easily. And why is the equator? Because the variation of temperature and the circulation of air masses is likely to be stronger and more important toward the equator.
Okay. Okay. So finally, it would be easier and mostly concentrated along what would be a Mars tropical latitudes.
Yeah, but an interesting fact is also that the lightning activity on Mars what's called polar wander.
Yes.
If you look at Mars, I don't know if everybody's familiar with that, but the equator where it is now is not where it was, most likely because of volcanic activity. When you have something like Olympus Mons, which is a huge landmass, it's likely to have tilted to be able to conserve angular momentum and move it toward the equator. So if Olympus Mons had started in the current north, if a few billion years ago Olympus Mons was created in what was then the northern hemisphere, then it could have rotated to the equator.
Okay. Yeah, that's nice. That's because I'm interested in that because I work on paleomagnetism and magnetism of rocks. And there's a big mystery about how how rocks in Mars are so magnetic. They are 10 times to 15 times more magnetic than the equivalent rocks on Earth. And one of the few natural processes to do that is lightning.
That I did not know. I do know that they are much stronger if you look at the remnant magnetism. So one thing is how strong was the dynamo when it started.
Yeah, but that's it. So either you have a much stronger dynamo, or just you have lots of lightning.
That's interesting. Because I mean.
And this likely would have stopped exactly when you have the two big craters that occur exactly after the geodynamo goes up and the atmosphere goes up. So somehow it coincides in time. If the end of the geodynamo and the end of the lightning, as you said.
Yeah. Well, the only thing I'm going to say is I can stop sharing the screen. Sorry. I'm presenting. Stop presenting. Sorry, I'm just seeing now the so the fact that we call it geodynamo is interesting because it's not geo. If anything, it would be an aerodynamo, Marsodynamo, because geo is very Earth-centric.
That's right.
So, and I make the mistake all the time, and I've been corrected I don't know how many times. That's why when I plotted the wet Mars, I put AAL above areoid level instead of above geoid level.
Okay.
So that's why I try to be a bit careful with those. Martian scientists can be really picky.
That's right. But anyway, it's in the magnetic dynamo of the planet. So
when I introduce that to my students, I tell them what would happen. I ask them what would happen if you had a compass and you were walking the surface of Mars. How would you find the north?
Yeah, it's hard.
Yep. Yes.
Okay, thank you very much.
Sure thing.
Hi, Jeremy. This is Rachel. Very interesting talk. I enjoyed it very much. Thank you for it. So if I got it right, and I think I didn't actually, one of the possible reasons for not having lightning in Mars is related to the concentration of atomic oxygen. Is that right? Could you please explain it again?
Yeah, of course, I can go there a little bit. So the biggest reason for Mars is meteorological. And actually, even more transparently, we don't know, because everything says we should have lightning on Mars. So so atomic oxygen, the presence of atomic oxygen lowers the conditions. It basically eases the creation of lightning. It makes it easier. If you look at this criteria I was looking at, if you add atomic oxygen, you make it easier to create lightning. And that's why on Mars is one more reason why you should have it. And by comparison, if we look at Earth, one basic photolysis is a way we get atomic oxygen in the E regions, and that's where most likely where we may have a decrease, or where we can initiate some of the discharges I was looking at. The sprites, the altitude, where they are initiated, also correspond where we start having a significant amount of atomic oxygen. So that's one more reason why on Mars we would have lightning. The reason why we have not so far is, I believe, because we've looked at what we call lightning on Earth, which are those highly energetic channels. Those have extremely strong signature. An interesting aspect, and pretty sure there is also one of such network in Brazil, but the lightning mapping array uses the VHF frequencies to detect lightning. I asked why VHF, and the answer was, well, because you can pick whatever you want with lightning, and that was an empty TV channel where we were.
Yes, exactly.
So the question is, well, are all these charges like that? Because if they are not, then there is absolutely no reason why, if we look for this lightning rather than sprites or jets or streamer, we would probably not detect them.
Mm-hmm. You're right.
So there is a lot of experiments looking not at lightning, but at weaker, less energetic discharges. And that would be the main reason why they may be there, we don't see them. And if they are not there, I still have no clue why they are not there.
Okay. I agree. Thanks.
Sure.
We are running a little bit late, so I think we just will have time to one or two other questions. Anyone? I think if not, given that we are already past the time that I that I am aware that we are allowed to be live, so I'm just going to go ahead and thank everyone for coming, especially Jeremy. And well, yeah, obrigado, pessoal, por vir para o seminário.
Yeah. Hi, everybody. I hang up if I find out.
Yeah, like if you want, yeah, we can.
I can hang out. I can talk to you.
Yeah, let's hang out. Why not?
But I have so if you have an interested, if people are interested, I was trying to see, can I share a document, a PDF
you can
inside inside the invitation, the iCal invitation?
I think you can. Yeah, sure.
Let me see. Let me see. That's my calendar. Okay. Appointment accepted. Propose. I'm trying to see, because this article in the Brazil, in the Scientific American in Brazil, I was able to retrieve it. So actually, I don't know how to do it. Darn. What is it? Invite?
I have no idea.
Anyway, so
you're asking the wrong person.
Anyway,
if you just sharing the link might work. Ah, that would be nice.
So okay, that's good. So I'm gonna do that. So Richard.
Yeah, just send him to Richard, and he will do it.
You see, new mail. Richard. Binger@usp.br. Okay. That is scientific. It's very hard to look for an article in Portuguese when you don't speak Portuguese.
That is true.
Mm-hmm. Okay. Sure. Bye.
Just ending the YouTube.